This is one of the most expensive fuels on Earth, costing around $8,000 per gram. A piece no larger than a thumbnail can keep a device running continuously for decades without ever needing a recharge. Voyager relied on it to fly out of the solar system, and Curiosity used it to trek across Mars for over a decade. Without it, almost all of humanity's deep space probes would be completely grounded. This extraordinary material is plutonium-238, a radioactive isotope with a half-life of 87.7 years. Plutonium-238 has one primary superpower. It generates steady, continuous heat. Just 1 gram outputs about 0.5 watts of thermal power, hot enough to burn if you touched it. This heat doesn't fade in freezing space or vacuum. It only slowly declines over its 87.7-year half-life. To convert this heat into electricity, space probes use a device called a thermocouple, which joins 2 different semiconductors together. One end touches the hot plutonium core, while the other is exposed to the extreme cold of outer space. Once this temperature difference is established, electric current flows automatically. The mechanism is brilliant. It has 0 moving parts, no combustion, no chemical reaction, and requires no maintenance. This system is known as a Radioisotope Thermoelectric Generator, RTG, commonly called a nuclear battery, first developed by U.S. national laboratories. In the 1950s, the first RTG-powered satellite launched in 1961, generating just 3 watts of electricity. Today, a single RTG unit can output 200 to 300 watts. Its energy efficiency isn't actually high. Only 6 to 7% of the heat is converted into electricity, with the rest lost as waste heat. It needs no sunlight, ignores dust storms, and operates easily at temperatures below -200 degrees Celsius. As long as it decays, it keeps supplying power, which is exactly what deep space exploration lacks most. Sunlight intensity drops drastically with distance. By Jupiter's orbit, sunlight is just 1/27th of what it is near Earth, and further out at Saturn or Uranus, solar panels are practically useless. On Mars, there's sunlight, but severe dust storms can completely cover solar panels. Spirit and Opportunity were solar-powered rovers. Opportunity was permanently disabled when a global dust storm cut its power completely. RTG-powered probes, however, don't depend on the weather, day or night, storm or clear skies. Their power output remains rock solid. When Curiosity landed on Mars, its RTG stably output 110 watts, keeping it operational through -90 degrees Celsius nights and ready to climb rugged slopes the next day. But deep space exploration faces a massive hurdle. Supply is dangerously scarce. The whole process takes 2.5 to 3 years. In the first few years, Oak Ridge produced only a few hundred grams annually. Recent targets aim to reach around 1.5 kilograms per year. That might sound like a lot, but a large probe like Galileo required nearly 16 kilograms for a single mission, more than 10 years of Oak Ridge's entire output. Engineers must queue up for strictly rationed allocations. Due to shortages, some exploration missions were forced to switch back to solar power, sacrificing flight range and mission lifespan. Yet, despite how hard it is to obtain, plutonium-238 has powered almost the entire history of deep space exploration for half a century. Launched in 1972 and 1973, Pioneer 10 and 11 relied on it to become the first probes to fly past Jupiter and Saturn, paving the way for Voyager. And in 1976, the twin Viking landers relied on it to explore the surface of Mars. Launched in 1977, Voyager 1 and 2 relied on plutonium-238 to fly past Jupiter, Saturn, Uranus, and Neptune. Today, they have pushed past the edge of our solar system into interstellar space. Nearly 50 years later, Voyager is still transmitting signals back to Earth. As their power wanes year by year, engineers are forced to shut down instruments one by one just to keep them alive a few years longer. The Galileo probe also used it to study Jupiter and its moons in depth. Ulysses relied on it to map the sun's polar regions for the first time. The Cassini spacecraft, launched in 1997, explored Saturn for 2 full decades. In 2017, to avoid contaminating Saturn's potentially life-harboring moons, engineers intentionally plunged Cassini into Saturn's atmosphere to burn up completely. The New Horizons probe relied on Pu-238 to take humanity's first close-up photos of Pluto, revealing its iconic heart-shaped ice plain before flying deeper into the Kuiper Belt. Modern Mars rovers like Curiosity and Perseverance use multi-mission RTGs, MMRD. Pulled by this small block, they run 24/7 without being stopped by dust storms or cold Martian nights. Even Perseverance's MXIE experiment, which generates oxygen from Martian carbon dioxide, depends on this nonstop power. Going back to the Apollo moon missions, Scientific stations left on the lunar surface relied on Pu-238 to keep operating through the freezing, fortnight-long lunar nights. Remarkably, Pu-238 even entered medicine in the 1970s. Doctors implanted Pu-238 nuclear-powered pacemakers into heart patients, providing steady energy meant to last a lifetime. However, tracking and recovering radioactive material inside human bodies proved troublesome, and the technology was phased out as lithium batteries improved. A dramatic accident in 1964 completely redesigned nuclear battery safety. A transit navigation satellite failed to reach orbit and re-entered over Madagascar. It burned up in the atmosphere, dispersing nearly 1 kilogram of Pu-238 across global air currents. Following this incident, the safety philosophy shifted entirely from burn and disperse to complete containment. 4 years later, this new design was put to the test when the Nimbus B weather satellite suffered a launch failure. The rocket was aborted 2 minutes in, plunging into the Pacific off California. Fortunately, the plutonium capsule was recovered from the ocean floor completely intact without a single leak and was even refurbished for a later launch. During the famous 1970 Apollo 13 emergency, the lunar module's RTG unit crashed into the deep Pacific Trench and remains safely sealed on the ocean floor. Over the past half-century, nuclear fuel casings have never failed again. Today, plutonium cores are encased in iridium alloy and wrapped in high-temperature graphite blocks, specifically engineered to withstand rocket explosions, atmospheric re-entry, and ocean impacts. Future demand will only grow. NASA's upcoming Dragonfly mission to Saturn's moon Titan, a dark world shrouded in thick atmosphere, will rely entirely on Pu-238 to fly and explore today. Only a handful of nations have the capability to mass-produce plutonium-238. Whether a proposed space probe receives a plutonium allocation often decides if the mission can even happen. How far humanity can venture into deep space depends largely on how much of this palm-sized radioactive metal we can produce. Unobtrusive as it is the silent engine driving our search into the unknown. And as long as production keeps up, humanity's journey through the solar system will never stop.